Well, ladies and gentlemen, welcome to our fourth video. We've survived our first week of our new flipped classroom, and hopefully it's about Sunday night when you're watching this video and getting ready for a new week of classes. Our title today is Factoring with Higher Powers, and this is, I think of this as our factoring finale. We're kind of going to put everything together that we've ever learned about factoring. For instance, with respect to our GCFs, just real basic review. If I gave you x squared minus 3x, we've got a GCF of x, and as we pull that out, we're left with the quantity x minus 3. Or perhaps we could talk about dots, and we say if we had x squared minus 16, that is a difference, emphasis on the word difference, of two perfect squares, and so that factors into x plus 4 and x minus 4, and certainly if we foiled those two guys together and cleaned it up, we'd get our x squared minus 16 here. Now just a little tidbit here, if we did change that to a plus sign, this would no longer be the difference of two perfect squares, it would be the sum of two perfect squares, which there is no factoring trick for, and that would now be non-factorable now. We could talk about just a traditional a traditional trinomial x squared plus 6x plus 8, and we're trying to think of two numbers that add up to 6 and multiply to 8 at the same time, and I came up with x plus 4 times the quantity x plus 2. And then we moved on and we said, well, that a value is not always going to be a nice 1. Sometimes a may make it a 2 or a 3. And 2x squared plus 7x plus 3 is an example where we would do some guessing and checking. We know that it's got to be 2x times x because those are the only two factors that give me 2x squared. And then we kind of play around with the factors of 3. With a little bit of practice, I ended up with plus 1 and plus 3. And you'll notice if I take my outer terms, I get 6x. My inside terms give me 1x, and if I add the 6x to the 1x, it checks, and I get my 7x. And then last but not least, our last lesson was on grouping, and that was traditionally for polynomials that had 4 terms in them, and we talked about how we were going to take a GCF out of the first 2 terms, and then a GCF out of the second 2 terms, and etc., etc. So today you're going to see a little of all of these techniques. We're going to throw a little of everything at you, and we're going to see a lot of GCFs, we're going to see a lot of difference of two perfect squares, and so on. So let's get warmed up. Okay, our first example here today, and we really want to emphasize today is this little words of wisdom up here. Always look for your GCF first. If we can get ourselves into a habit of identifying and pulling out that GCF right away, it's going to make a lot of these problems significantly easier. So as we look and we scan through this first problem, and we're trying to ask ourselves, what do all 3 terms have in common? What are they all divisible by? And it looked like each term had at least an x squared and at least a y squared. So I'm going to go ahead and I've pulled out x squared, y squared as my GCF. Okay, and now we're just going to go through and we're going to divide each of these terms one by one by x squared, y squared, and we're going to ask ourselves, what did we get after we divided by x squared, y squared? And again, as what I'm showing you here in orange is not something that you have to show me, but I think it's very helpful as you try to decide what's left here in the parentheses. So the first term, x to the 4th divided by x squared, is going to give me x squared, and the y squareds cancel out. In my middle term, I'm going to say that 4x cubed y squared divided by x squared y squared is simply minus 4x. And on the last term here, I had just minus 12 after I divided. Remember, we aren't quite done yet. As you look inside these parentheses here, we have a very nice trinomial, and we're just going to try to ask ourselves what 2 numbers, whoops, did you see that mistake? Don't want a squared there. Holy smokes. We're trying to think of what 2 numbers add up to negative 4 and yet multiply to negative 12 at the same time. I'm going to go with minus 6 times a positive 2. And now this whole expression right here is what I consider to be factored completely. And we'll go ahead and we'll put our little stamp on it. FC with an exclamation part. We are completely factored now. For our second example, I want to look at the trinomial x squared minus 13x plus 36. And perhaps you were wondering at the beginning of today's lesson what we really meant by higher powers. But what's going to happen here today is instead of staying with x squared minus 13x plus 36, I'm going to grab my eraser here and I'm going to tweak the exponents just a little bit. Instead of, let's see, whoops, that's not working. Whoops, timeout. Okay, we're back. My eraser's not working really well, so what we're going to do is we're just going to cross that guy off here, maybe. We'll cross him off. What we're going to do today is we're going to take a look at x to the 4th minus 13x squared plus 36. And this is what we meant by taking a look at higher powers today. We're going to see, this is what we consider a 4th degree polynomial because the biggest exponent you'll see here is a 4. And we'll also make a note that we are expecting 4 solutions from this polynomial because of the fact that the biggest exponent we see is a 4. Also, another bit of information, because it's equals to 0, we are assuming that we are not only factoring this one, but also we're going to move ahead and solve it as well after we factor. So, as we try to factor this, we're trying to think of what term times what term here would produce a product of x to the 4th, and I'm going to go with x squared times x squared. I think you'd agree that x squared times x squared would give me x to the 4th here. And then we're going to stick with our same technique of trying to think of two numbers that add up to negative 13 and yet multiply to positive 36. I came up with negative 4 and negative 9. Okay, now we ask ourselves, are we completely done factoring? And I think you'd agree that we're not. We have a difference of two perfect squares. I'm going to say x plus 2, x minus 2, times the quantity x plus 3, x minus 3. Get used to seeing a lot of difference of two perfect squares. We're going to see a lot of those tonight. And now as we get ready to tee these up, you do see the 4 solutions that are coming. We've got x equals negative 2, we've got x equals positive 2, x equals negative 3, and x equals positive 3. Now one thought that I'll leave you with here is ask yourself, what do you think this graph looks like? Is it a traditional parabola? Keep in mind that we're claiming it has 4 solutions, which means that it has to cross the x-axis 4 times. If you're curious about that, go ahead and enter this equation into your calculator and take a look at it. Our third example looks like x to the 5th plus 21x equals 10x cubed. And again, they're asking us to not only factor but to also solve this one. And I'm going to make a note to myself here off to the side that I am expecting 5 solutions when I'm all done because of the fact that the highest exponent I see is a 5. The first mini bear trap is the fact that not all the terms are on one side. So I'm going to try to subtract this 10x cubed to the other side, and I'm going to be very careful as I put it in the middle of those 2 other terms. Standard form implies that we start with the term with the biggest exponent first, and then we work our way in descending order from left to right. A couple of slides ago, we mentioned that we want to get in the habit of always looking for a GCF first. And I think you'll agree that we do have a nice GCF of x. And as I pull that x out, dividing the first term by x gives me x to the 4th. The middle term becomes 10x squared. And that last term becomes a positive 21. Okay, now we're going to be very careful not to lose that GCF. We mentioned the last week in class that if our GCF is a variable, such as x here, we've got to be very careful not to lose it or throw it away. The next thing I'm going to do is we're going to say, okay, an x squared times another x squared gives me x to the 4th up here. And then I'm just going to try to think of 2 numbers that add up to negative 10 and yet multiply to positive 21. I would encourage you to maybe pause the video at this moment and try to think of those 2 numbers on your own and then go ahead and click play again. I came up with negative 7 and negative 3. Now you notice the 7 is not a perfect square, neither is the 3, so I do not have a difference of 2 perfect squares. I am completely done factoring and I'm ready to tee this up. On the far left here, I'm going to say that x equals 0. Inside here, if I said that x squared minus 7 is equal to 0, that implies that x squared is equal to 7, and then x is equal to radical 7. And then last but not least here, x squared minus 3 equals 0. X squared is equal to 3, and therefore x is equal to radical 3. Now perhaps you've noticed an error that I've made, and I hope you've jumped all over that. I've tried to make a point here that remember we were expecting 5 solutions, but I only have 3 solutions listed here. What am I missing? What am I missing? Well, do you remember that when we take the square root of both sides here, we've got to remember to incorporate or include our plus or minus sign. And the same goes for here. Every time we take the square root, we're going to make sure we have our plus or minus sign. So now we do have a grand total of 5 roots. 0 is a root. Positive radical 7 is a root. Negative radical 7 is a root. And then positive radical 3 and negative radical 3 are all roots, thus giving us a total of 5. Our fourth example is a very interesting problem, and you'll notice the title that I've given this one. We say that this polynomial is partially factored already. They've done some of the heavy lifting for us ahead of time, which was very nice of them. And now they're just asking us to finish factoring it if possible, and then to tee it up and solve it. So as I analyze this first trinomial, x squared plus 5x minus 7, I'm trying to think of two numbers that add up to 5 and yet multiply to negative 7. I tell you, we could sit here until the cows come home, but I don't think we're going to be able to think of two numbers that satisfy those two requirements. So what you're going to notice is, unfortunately, this first trinomial is not factorable. And if it's not factorable, what are our options for solving? Well, you've guessed it. We're left with the quadratic formula. And so I've got to set up my quadratic formula. X equals negative b plus or minus the square root of b squared minus 4 times a times my c value. And that's all divided by 2 times a. Feel free to grab your calculator here to help you clean up some of these numbers. Inside that radical, let's see what we got here. I've got 25 plus 28, which is going to give me a grand total of 53 divided by 2. Probably the best news coming out of this problem is that the 53, the radical 53 is not simplifiable, I guess. So right there is our final answer for this side of the t, and that provided my first two roots. On the other side of the t, we have a much friendlier problem to work with. We're simply going to take the expression x minus 2, set it equal to 0, and x equals 2 is one of our roots. Now we do have a grand total of 3 roots here. X equals 2 is one of them, and then we could say that negative 5 plus radical 53 divided by 2 is a root. Let me write that out. And then we could also say that negative 5 minus radical 53 divided by 2 is the last and third and final root. Well, we've got a few more problems to go over, and before we do so, I just want to have a mini discussion, kind of a mini side lesson on perfect squares. And notice here, I've set you up, refresh your memory with the first couple of perfect squares. We know that 0 and 1 and 4 and 9 are perfect squares. You know, why is 9 a perfect square? Well, there is a number, when multiplied by itself, that produces 9. And of course, I think we'd all agree that that magical number is 3. 3 times 3 is 9. What I want you to do right now is hit the pause button and generate a list of perfect squares that come after 9. Okay? And then come back, hit play, and see if you and I have the same list of perfect squares. Okay, maybe you got a list like I have here on the left-hand margin, 16 and 25 and 36 and 49 and et cetera, et cetera. And that's a list of numbers that we want to be very, very comfortable with as we go into our deeper discussion about perfect squares. I want to ask you, is x to the 6th a perfect square? Question mark. Well, we have to ask ourselves, is there a term when multiplied by itself that produces a product of x to the 6th power? And I would say there is a term that I can think of. I would say x to the 3rd times itself produces x to the 6th. If you recall, when we're multiplying like bases, we're simply going to grab those exponents, add them together to get our new exponent of 6. So here's the danger of this discussion. Am I trying to tell you that the number 6 is a perfect square? No, I'm not. The number 6 by itself is not a perfect square. But what we are trying to say is that x raised to the 6th power is a perfect square. For instance, let's take a look at another example. Is x to the 8th a perfect square? I would say yes, it is, because x to the 4th times x to the 4th produces x to the 8th. Therefore, x to the 8th is a perfect square. Now, don't try not to confuse that with the idea that am I trying to claim that 8 as a number is a perfect square. No, 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 no. 8's not a perfect square, but x to the 8th is a perfect square. Let's try a couple of more of those rascals. Is x to the 10th power a perfect square? Can you think of two terms that are identical to each other that could multiply together and give you x to the 10th? Who would you throw in these spaces right here? Hopefully you were thinking of x to the 5th. So yes, x to the 10th is a perfect square. Now here's an even crazier example. How about x raised to the 2a power? This is a really wild one. Is x to the 2a a perfect square, yes or no? So we're trying to think of is there two terms that are identical to each other that I could multiply together to get x to the 2a? Maybe try this. How about x to the a times x to the a? You'll notice we are multiplying like bases, so all we have to do is grab those exponents, add them together, and you'll notice that a plus a is indeed 2a. So we can make the argument that x raised to the 2a power is indeed a perfect square. Okay, let's try to factor a couple more examples, and I apologize, I'm not exactly sure what example. I think we're on number 6. You can pick on me Monday in school if I'm wrong at that. But I want to try 4x to the 8th power minus 64. There we go. The one habit I want to continue to preach here is to get in the habit of looking for a GCF first and foremost. I recognize that 4 was my GCF. I factored that out, and I had x to the 8th minus 16. I then recognize that inside my parentheses here, I did have a difference of two perfect squares. When I look at x to the 8th power, I think of x to the 4th times x to the 4th. Of course, 4 plus 4 gives me that 8. And then that last term, I'm thinking plus 4 times a negative 4 would produce the negative 16 up here. And we're not quite done. Now, x to the 4th plus 4 is not factorable. However, x to the 4th minus 4 is another difference of two perfect squares, and I'm going to go with x squared plus 2 and x squared minus 2. And now we could put our official stamp on it and say that this expression here is factored completely. Let's try another one that was fairly similar to that last one. Let's take a look at a to the 8th power, which you'll hopefully agree with me, is a perfect square, minus, there's your difference, b to the 4th, which I hope you agree is another perfect square. So as we recognize here that we have a difference of two perfect squares, I'm thinking a to the 4th times a to the 4th would produce a to the 8th up here. And then we have our plus and our minus. And I'm going to say b squared times ab squared. Now, again, let me emphasize, when you look at when we talk about dots, d stands for difference, which implies we're looking for a minus sign. So once you see the plus sign here in this term, you know instantly that we're done factoring that binomial completely. But then we come over here and we say, okay, a squared times a squared produces a to the 4th, and then we've got plus b minus b. Now, we could put our stamp on this one and say that this bear is factored completely. Ladies and gentlemen, you're almost there. Hang in. Let's go get one more problem for the night. The last problem we want to attempt to factor today is certainly the ugliest one we've seen in a long time. The trinomial says x raised to the 2a power plus 4x to the a minus 32. And all they're asking us to do here is to simply factor it as much as possible. We're not going to worry about solving it. So this is a traditional trinomial in the sense that, let's focus on the positives first. Our leading coefficient, our a value up here, is a 1. And now we're going to try to think, all we have to do is think of two numbers that add up to positive 4 and yet multiply to negative 32 at the same time. Oh, did I forget to address that first term? In these first slots right here, I'm trying to think of two terms that I could multiply together to produce x to the 2a power. I'm thinking of x to the a times another x to the a. And just to refresh your memory, if we do multiply those two terms together, we would then add up the exponents, and a plus a does give me the 2a up here. Did you think of two numbers that added up to 4 and multiplied to negative 32? Perhaps we could say plus 8 here with a minus 4 right there, and I think you'd agree that they do multiply to negative 32 and add up to positive 4. So ladies and gentlemen, perhaps one of our uglier problems we've ever done. If you had questions and weren't sure about this one, we could go ahead and FOIL it back out as a method of checking it to see if it gave us the original problem, x to the 2a plus 4x to the a minus 32, and I think indeed you would get that result. Well, that brings us to the conclusion of our fourth video. Today's title was Factoring Higher Powers, and we looked at a lot of different examples. Some of our highlights today that were the fact that we saw a lot of GCFs, we saw a lot of difference of two perfect squares, and we saw some rather ugly trinomials. Just a quick checklist here as we get ready for a new big week. Our highest priority here early on in the week is to complete our test corrections. So if you haven't completed those yet, make that your highest priority here before school's over on Monday. Hopefully you can use your notebook as a guide. Hope maybe you can talk to some of your friends and then come and see me after school, and we'll take care of any unresolved problems. Also, you've got a new spiral that needs to be done. If we can turn that in on Monday, we're going to get plus 4 extra credit points. Also, when you walk in tomorrow, we'll get a new bear sheet with some extra credit questions to take a look at, and hopefully just have a real good week. Hopefully we're shooting for our best week of the school year yet. So ladies and gentlemen, I hope you had a good weekend, and I look forward to seeing you tomorrow.